So hello, everybody. Thank you for joining us. Now, if this slide might scare you, it kind of even scares me, even though I've had about 40 years of experience in the industry. These are basically all the different in-vehicle networking technologies that have been and/or are going to be implemented in automobiles, but not just automobiles, as we'll find out. But I mean, that's really the focus of what we're talking about here. And what we're really going to focus on here really started in the mid 1980s. This CAN networking, controller access network, first developed by Bosch, automotive company in Germany back in about 1986. Because really prior to then, I mean, well, obviously prior to the 1980s and so on, cars were a lot simpler. There was wiring, but it was all pretty much dedicated. Turn the headlights on, there's a dedicated light for the headlight. You know, you hit the brake pedal, there's a dedicated line that goes back to the brake light. That was okay until cars started becoming more sophisticated and getting more features. And so the first response to that was CAN, but there's been other responses to it. And there's reasons why. I'm not going to go through every one of these here. For instance, multimedia systems take a lot more bandwidth. So that's where this MOST protocol came in, for instance. And certain systems require more security inherently. So they might be put on systems using FlexRay networking, for instance. And even CAN has evolved to its current form, which is CAN-FP, CAN Flexible Data Rate. And another big thing, which I'm not going to be discussing here, and really hasn't seen a big implementation yet in the industry, is Ethernet. Automotive Ethernet, they refer to it as now, which to a certain extent operates the same as Ethernet, just in your enterprise and those types of networks, but a little bit slightly different implementation. But again, I'm not going to be going over that. And there's reasons why we'll also introduce Ethernet into automobiles. So really today, most cars are a hybrid of multiple networking technologies, depending on the systems that they're servicing. Oh, I'll also mention LIN. And again, I have another slide that's going to cover some of these more common ones, similarities and differences. So why CAN bus? As I mentioned before, the 1980s, for instance, every component was wired up to every other component. So you can imagine the cabling harnesses and all that kind of stuff were starting to get quite large, expensive, complicated, especially in terms of trying to troubleshoot when something went wrong. Heavy, you know, that's obviously an issue with cars. We want to make them as light as possible and so on. And so Bosch developed CAN, controller network, which is a bus topology. Bus means everything's connected to a common, if you want it, well, bus, but hate to define a term with the term, but sometimes it's referred to as a backbone or just a wire that runs throughout the system that all the devices will tap into. As I mentioned, Ethernet itself started out as a bus technology, for instance, and there's benefits for that and reasons why. All right, so CAN bus, so as I mentioned a moment ago, controller network, bus topology, it's a serial bus, meaning only one bit can be on the wire at a time. It's actually implemented with two wires, the bus itself, and then the nodes are typically in the automotive world, the node is referred to as ECU, electronic control unit, and they connect, you know, to each of those buses. They could physically be spliced in, okay, that way. Some implementations, they might just couple an inductive device on there to pull the signal off of the wire without actually cutting into it. But there also, we'll see in a moment, there also is a way to have like a hub where everybody connects. And even though it's still shared, and in some cases you might say broadcast medium, where when you put a signal out on the bus through your stub, it reaches every other node in the network without necessarily even being repeated. It just places the voltage on the bus and everybody sees that rise and fall of voltage and interprets it accordingly. Well, a couple of things I'll point out here, but we'll get into more details on the other slides. You can see it's two twisted wires referred to as CAN high and CAN low. And those are common colors when you're looking at schematics and stuff like that. Although the physical wires themselves are not necessarily that color, but in schematic representation and so on. Although this one is a little bit of a variant on the right here where, you know, yellow is orange and and greenish, I'll just say that, is blue, but don't get fooled by that. It's still. And we'll talk about how this operates, where one ECU puts a signal on the bus, the others, everybody will accept it, check it, but only the one that needs it receives it, which could be multiple nodes. There could be multiple ECUs that need that information, such as engine RPM level or something for what their function is. And so you could have multiple nodes that actually accept the message. And that's a part of the beauty of the CAN bus system is it's a broadcast. Everybody sees it, but only those that need something to do with it will receive it. The rest of them will ignore it. So some benefits of CAN bus, as I've sort of mentioned some of these already, it's simple and low cost. You might say, well, Ethernet already had a bus topology. Why not utilize that? Well, for one thing, Ethernet is not low cost. The CAN bus protocol is very streamlined. I don't know if you want to say simple. It's all relative, right? There are complicated aspects to it, but overall, the complexity is not too unwieldy. Centralized. Now, I got to be careful with this centralized aspect because really every node is a controller. It's not like a master slave tie system where you have one master that, and you have multiple slaves that communicate with it, but not necessarily to each other. Every node in this is a controller. I think the centralized aspect of it, what it's talking about here is if you notice this yellow device that is thinking about, well, it could be tapping in, and it could just use an inductive clip, like I said, to pull the signals off of the wire. And we'll talk a little bit in a little while about a CAN logger. So think about this as a logger that taps into the bus and can see every signal from every device. And so that's really the centralized aspect. And then it can start logging every message, and then you can do some analysis on that. And we'll talk more about that in a moment. It's a very robust system, and that's partly probably why Ethernet wasn't used, because especially if you think about the way that it operated as a bus. If you ever heard of thicknet, I used to deal with that a lot. It was a thin coaxial cable that was connecting using T's, but you could walk around and wiggle the T's around and stuff, and the network would go up, down, up, down, up, down. Now, if that was part of your braking network, that could obviously be a problem. So the way connections are made, the simplicity of the system. We'll talk about the signaling, the differentiated signaling it's referred to for noise immunity and all that kind of stuff. It makes it a very robust system. And it's not just for automobiles, by the way. This obviously shows a tractor here. Believe it or not, the Mars rover has a CAN bus in it. And there's reasons. It's for all these reasons, lightweight, simple, low cost.
Boeing uses them in commercial aircraft.
Commercial aircraft, yes. In industry, industrial applications where all the nodes need to be connected and be able to communicate with each other. So yeah, there's lots of implementations for this. And it's very efficient, as we'll see as we go through here, especially in the transmission of frames. It doesn't require retransmission in terms if there happens to be what Ethernet referred to as a collision, and we'll talk about there. So in that regards, since a frame doesn't need, if two nodes starts transmitting simultaneously, which is typical of a bus, in Ethernet, if they collide, then they both stop, back off, and retransmit. Well, that doesn't work too well for real-time applications where the information needs to get there in milliseconds or sometimes even less than milliseconds. And so there's a lot of reasons why it makes it more efficient. And I put this little thing in here. If you think about the CAN bus as like Christmas lights, a string of Christmas lights, I guess that's a good logical way to think about it, because you can run this all the way around your house. Imagine if you had to run a separate wire to each light in your house. Whereas now the wiring is different. That's why I say sort of, but that's a good way to picture it. And speaking of analogies, you could think about CAN bus in your car like the human body, where the bus itself is a nervous system, which translates signals throughout the body, and obviously those parts of the body, which in CAN bus is referred to as the ECUs, all can use that signal or not, like I mentioned before, because they're all interconnected on the same broadcast CAN bus. so they all can share information with each other. I gave a little example of that a moment ago. Modern cars have lots of ECUs. Your headlights, for instance, are an ECU nowadays. And think about all the things that a headlight can do nowadays. If you weight down the car in the back, some of the cars with the nose sticking up further can actually tilt the headlights down a little bit automatically. How about headlights that automatically dim or go to high beam and dim automatically? I mean, there's a lot of different examples if you talk about just what the capabilities of headlights are nowadays and why you need more intelligence to control them. And more intelligence means more connections, more information transferred, all that good stuff. And let's see, a lot of these things I've talked about down here in terms of you don't need complex dedicated wiring, it's broadcast domain. The CAN bus consists of 2 wires, CAN high and CAN low. And we'll talk about why that is again in just a moment. So you have somebody sending, everybody else will initially accept, so they'll start interpreting the data, but only those, first of all, that are checked good. There's error detection and such in the signal as well. And then need it will receive it, the rest will ignore it. Now, here's some examples. So a car doesn't have just one CAN bus. Typically it has multiple ones. I think in the project you're working with, I identified somewhere in the neighborhood of 8 different CAN buses, as well as other technologies, like I mentioned earlier, FlexRay, if more security is required, LIN, which operates a little bit differently. For one thing, it's a single wire. I know these all look like single wires here, but all the CAN buses, for instance, are dual wires, CAN high and CAN low. But LIN came into play because certain applications like moving your windshield wipers or something like that don't require a whole lot of information, so they don't need all the robustness and everything. So they'll connect via LIN over a single wire to a controller, but that controller, on the other hand, could also connect to a CAN because it's probably receiving its information from somewhere else to tell the windshield wipers when to start and stop. I'll talk slightly more about LIN in a moment, but here's an example of an ECU unit that actually can convert between LIN and CAN, for instance. And by the way, the reason different CAN buses, in addition to that, this one in this case talks about, well, there's a network for all your comfort interior items for controlling them. There's a separate one for the powertrain operation and so on, which could include braking, all that kind of stuff. And what you could end up with, and you'll see that in just a moment, different CANs can operate at different rates, both in terms of the speed that they operate, as well as the size of the data that they can carry and that sort of thing. And so you can have a central gateway, which I also noticed in the system that you're working on, there is. In fact, in that case, it's called a central security gateway, a CSG, but this gateway interconnects the CAN and can actually do speed and protocol conversion. So if this is a low speed CAN, that's a high speed CAN, it'll buffer in and then resend it out. And in some cases, reformat it based on, we're going from CAN protocol to the extension of CAN FD, for instance. So it can do some translations of that as well. And so just an example of what you might find. Again, a simplified example, but an example nonetheless. Okay, so this talks about some of the flavors of networking. It doesn't cover all that were in that second or third slide that I showed you here. And I'm just going to highlight a few things. I put a lot more notes on these slides, verbiage, because I didn't want you to have to write down things feverishly, and I wanted to make sure I got it all in there for the handouts that you got. So, but I'm not going to cover everything. But high-speed CAN is a version. They also call it classical CAN. That can operate from 40 kilobits to 1 megabits. And there's a second generation of that referred to as CAN FD, CAN flexible data rate, that can actually extend the speed up to 5 megabits. Whereas low speed CAN operates between 40 kilobits and just 125 kilobits. Now, the low speed CAN is different, and you'll see I got a little diagram talking about that in terms of how it's engineered. So to speak, it's more fault tolerant. And in that case, each CAN node has its own CAN termination. We'll talk more about termination in a moment as well. And then another flavor, like I mentioned, LIN, local interconnected network, is a supplement where we can use less wiring and cheaper nodes, single, not two wires, for applications that don't require the robustness and don't have quite as much information to transfer as I gave you with the windshield wiper example earlier. And then there's also automotive Ethernet. So some of these ECUs are getting quite sophisticated, even providing advanced driver assistance systems, ADAS, which are interconnecting lots of LiDARs and radars and cameras. And you can imagine the amount of data that needs to be moved with those. And so CAN-FD operating up to 5 megabits may not meet the bandwidth requirements of some of these systems. So we're working on implementing automotive Ethernet now to support those higher bandwidth requirements. Well, I'm not sure if you guys have studied networking to the extent of standards, the OSI model, Open Systems Integration Model from the ISO that was defined many, many years ago, I think probably back in the 1970s, as a way to break up functionality. So you can, like, physical layer is your cable and the signals on the cable and how those signals are formatted. I'll talk in a moment about CAN bus 2-wire high-low system using differential signaling. Those are all physical, as well as, you know, what type of connector are we using and those types of things is the physical layer. The data link layer are how messages are formatted. And also, how do I get my message out on the wire? How do I determine who it's from, what it is, who it's for, all that good stuff. So you start to get into the messaging format and everything at the data link layer, which pretty much just covers those two lower layers. But as you can see, there are certain higher layer protocols that will cover, and you don't always have to cover every layer of the OSI model. Some more sophisticated protocols like TCP/IP and so on, and all the applications that are associated will utilize where CAN. For one, CAN doesn't use the network layer because really there is no networking. In other words, routing. Yeah, you're not going to send a CAN message from one car to another car, for instance. Even though nowadays with what we call V2X, vehicle communication over the air to anything, it may seem possible, but it's just not implemented that way. By the time it gets out over that air, it has nothing to do with CAN anymore. But the higher layer protocols, onboard diagnostics, those are typically used for automobiles. J1939 is similar to ODB, but for large trucks, which I think is more relative to the project that you're going to be doing, as well as others. I haven't listed all of them that would cover other, application layer functions for CAN. And as you can see, the main suite of CAN protocols developed by the ISO is the 11898, but then the variations, -1 covers the data link layer, -2 covers the physical layer, and so on. So a CAN node, again, also in a car, it's referred to as an ECU, electronic control unit. And I mentioned earlier, it's a distributed system in terms of control because there's no central controller with CAN. Every unit is a controller. And every unit therefore has the right to both send and receive when it decides to. It doesn't have to wait for a poll. It doesn't have to do anything like that. So the CAN controller is part of the CAN node that operates at OSI layer 2. Or you can say the microcontroller or the processor is what deals with the upper layers of the OSI model. Once it decides, remember, every device on the bus will see the signal, but only certain ones will decide to do something with it. At that point, it gets passed up the stack, so to speak, to the microcontroller and the application that CAN is actually supporting. And then at the physical layer, we have the transceiver. So that's a transmitter receiver converting the signal through a media access unit, whatever the format of the bits were in, that needs to reformat them to get on the bus and format the electrical levels and all that kind of stuff appropriately. And that would obviously be the OSI layer 1. By the way, I think on the previous slide I mentioned that the physical layer was described by 898-2. Well, the low speed CAN physical layer, the one with that fault tolerance built in and all that kind of stuff, like I mentioned, is actually 1198-3. So good trivial information for you guys some night while you're partying. All right, so a little bit of a busy slide. First of all, look at it in two halves, the left side and the right side. So this shows you the signaling, the high speed versus the low speed CAN. And in fact, this is the actual 11898-3 low speed CAN topology, where a main difference is you can see that each node is terminated with a resistor. And that's where the fault tolerant aspect comes into it, for instance. Because with high-speed CAN, we have a single bus that just has a terminating resistor at the ends. Well, what happens if the wire breaks here? The whole bus basically goes down because of the whole reason the terminating resistor is there is because it matches the characteristic impedance of the 22 gauge wire, where if there was nothing terminating that, dissipating that signal, it would reflect back and interfere back with its original signal. Whereas in CAN low speed, since it's terminated everywhere, you have that signal dissipation at the end of every link. And that aspect of it does make it more fault tolerant. Now, quite honestly, you could do the same thing with high-speed CAN. I think you'll find that a lot of, and I know that you have your CAN hat unit gives you the capability to terminate at the end inside that CAN hat. For each of the two CANs that it interfaces with, it's not going to hurt to terminate at every node like this. It's just high-speed CAN doesn't necessarily require. Typically, the nodes that are connected to the ends are the ones that have the terminators. I mean, typically you're not going to solder a resistor there. It's not to say you couldn't, that would work, sure. And these are, by the way, 120 ohm resistors because they match that characteristic impedance of the wires of 120 ohms. Now, let's look at the actual voltages. These are the signals, and this is where the CAN high, CAN low, with high-speed CAN, the maximum voltage, well, the medium voltage is 2.5, the maximum is 3.5, and the low is 1.5. When you're at the medium level, which, by the way, the voltage is held there when nothing is happening. And that actually, they call it recessive state, which the recessive state is actually a logical 1. You can see up here, 1 is when both the CAN high and CAN low are in their recessive state. They're both holding their respective lines. Remember, these are two separate wires at 2.5 volts. By the way, two separate wires. And what's not depicted here, which I haven't mentioned yet, these are twisted together. Part of the reason for twisting them is to hold them together. Yeah, but the other part of them is that also helps with noise immunity because it keeps the cables close enough together. So when a voltage spike from whatever, right, it could be from your cell phone ringing or something like that, that induces a voltage because it's not shielded wires. So it's possible, but let's say you get a 0.5 voltage induced in this pair, this twisted pair. Well, both CAN high and CAN low are going to go up by that 0.5. And it looks at the difference between them. Well, in a recessive state, there's still no difference, even though their voltage exceeded by 0.5. And same thing with what's called the dominant state, which represents a logical 0, where in this case, 3.5 and 2.5 for CAN high. Again, they'll both just go up by 0.5. So the difference between them is still going to be 2 volts regardless. And so that's the differential signaling aspect of it that helps them tolerate noise and just make the whole system more robust. So try to keep in your minds and remember, the dominant state is the higher voltage and it represents a 0. The recessive state is the medium voltage and it represents a 1. And by the way, you might be wondering, when there's nothing there, why don't I just have no voltage on the wire? Because if the wire gets broken somewhere, that will cause no voltage in a certain part. And if no voltage is your medium level, how do you know that something went wrong? And so it helps with that aspect of things as well. The last thing I'll point out on this slide is with low speed CAN, and again, that's the 11828-3 standard, not the lower speed, high speed CAN that was -1, or I'm sorry, -2. But, talking about this more robust system, its voltage states are just a little bit different, a little bit higher than and again, that also would help, with the robustness, which is part of the reason why we might implement low speed CAN again, but as long as the bandwidth is enough to support the type of ECU that we're using.
Quick question, Larry.
Yeah.
Is CAN wire not only twisted but shielded?
No, it's not shielded. Not shielded. That doesn't need to be, and that's the beauty of this differential signaling technique.
Okay.
Yep. And I'll show some examples of the physical wiring here in a moment too. Thanks for asking. All right, well, let's look at a CAN frame. Okay, so now we're up at the data link layer level, right? And so that's where we actually frame the bit into fields. If you've studied protocols and stuff like that, this is something that's familiar with you. The fields are generally broken up. Some of the fields are used by the physical layer, for instance, such as the start of frame field, and even the arbitration ID to a certain extent, although that's shared somewhat with the data link layer as well. Cyclic redundancy check to make sure that none of the bits got flipped. That's a polynomial type of calculation. If you're familiar with that, it's a 16-bit CRC. And then other ones are specific to the data link layer and processing of the messages, such as the data lane, the data bytes themselves, whether or not we're acknowledging, and so on. Yeah, so that's the difference. The bottom part are the ones that are essentially, it says processed by software, but processed by the data link layer. Where, of course, the physical layer sees everything. So let's continue this a little bit. The identifier, the ID, it's called the arbitration ID, and you'll see why it's referred to that in a moment. It could actually be either 11 bits, giving you up to 2048 combinations, or 29 bits, and that's standard, by the way, or 29 bits, which is extended. And you can see that could go up to what? 5,536,000,000 combinations. So as you add more functionality and even more ECUs, even though there is a practical limit for the number of ECUs that you'll have on any one CAN bus, but again, a vehicle will have multiple CAN buses, but multiple functions may need more than one ID, even from the same node or same ECU. So there was a need to extend that field. And then if we, let's see, arbitrate, and I'll talk more about how that arbitration ID is used to determine who gets to keep sending. If two nodes try to send simultaneously, well, who wins? Okay, in Ethernet, we called it CSMA-CA as carrier sense multiple access with collision avoidance, or CD, collision detection, which was the current versions of Ethernet utilizes. CAN uses something a little bit different than that, because in both cases with Ethernet, it's what's called destructive. In other words, if there's a collision, everybody stops sending and has to resend. Where with CAN, the way that this arbitration works, it's referred to as real time, meaning it's not destructive. Someone will win if two start, but the one that wins just keep on transmitting, doesn't have to retransmit. So that's a very important function. It's actually pretty genius the way they design this, especially in its simplicity. Sometimes there's genius in simplicity as well. Data link will tell you how much data, typically or originally, especially the data field was 8 bytes, but now with CAN-FD, so it's not just flexible data rate that offers higher data rates and stuff, but also extends the data field even up to 64 bytes. And that will be indicated here. And then I just mentioned about the data bytes. And then there's also a way, and that's with the status, and we'll get to that in just a moment, especially validating the cyclic redundancy check, for instance, that can determine if any bus errors are existing. Oh, a little bit more detail now on the frame. And again, I'm just going to highlight some things here. So again, between frames, we hold the voltage at the recessive or 1 level. And I mentioned a moment ago why we do that even when we're not transmitting any data. So what happens is when we start to send a frame, we pull the line, both the high and low lines, to the dominant 0 state. For high-speed CAN, that would be 3.5 volts and 1.5 volts respectively on the CAN high and CAN low lines. So everybody, it's like a wake up, right? It's only 1 bit. Wake up, everybody. Okay, there's the next bit that's coming is the first bit of the ID, right? And that's the frame identifier. Now, one of the main things of the frame identifier is to determine the priority of the message. And that also determines who gets to keep sending, if 2 send simultaneously. How likely is it that 2 will send simultaneously? Well, obviously, it just depends on how many ECUs and the speed of the medium and all that kind of stuff. And I kind of got a slide that talks about some of that as well. And so we'll get more on remember, the ID is also referred to as the arbitration field, how that arbitration works with the prioritizations and all that. There's also a way to request a node to send data. So there's an RTR bit. Okay. The control, I've talked about that. It's kind of broken up into some different bits. There's the IDE bit, which determines if it's an 11-bit ID. Whereas I mentioned before, it could also be a 29-bit ID where that IDE bit would be a 1 to indicate that. And it also contains the data length code to specify the length of data. Data we talked about, of course. I'm going to get a little bit more some examples of that because, from what I understand, you're building data, CAN data messages in your system that are going to send into the simulated truck. So it's important for you to know a little bit more about how that data can be formatted and various things like that. I also mentioned for error checking on the bit level, there's a cyclic redundancy check field, so CRC16. And acknowledgement, so you can acknowledge even at the layer 2 data link layer of the OSI model that the data was received correctly, and then end of frame. So because I'm not going to get, there's a lot of electrical characteristics and stuff related to CAN that really you don't need to know, engineers, unless you're actually, I don't know, building an ECU or something like that, or just engineering a CAN network for an automobile or truck or whatever it might be. There's a lot of electrical characteristics and property so one of them has to do with bit stuffing. So you don't get too many 1s or too many 0s in a row, because that holds the line at a certain level and it can start to cause all the nodes to lose synchronization, because nodes synchronize through the rising and falling edges of each bit. And if they don't rise or fall for some time, you're going to lose your synchronization, because there is no central synchronization entity besides just the data bit stream, for instance. And so the way that we flesh out when the end of the frame is, and then when no more bit stuffing is going to occur, is if we send 7 recessive 1 bits, because that would never happen during the transmission of the frame, because bit stuffing would prevent that from happening. I believe bit stuffing starts happening after six bits. And then I mentioned before, interframe space. So in between frames, we hold the line in the recessive or 1 state, which basically essentially matches the end of frame. We just leave it in that state until the next node comes on and either changes the state to a dominant 0 to start transmitting again. So the arbitration that I mentioned before, so multiple units, they're listening, they see or detecting, whatever you want to say, that the line's in the recessive state. So it means it's idle and it can now start transmitting. So if one device starts by himself, sends that start of frame, which is a dominant state, a 0, changes the state from the recessive to then. And if everybody else sees that, nobody else is transmitting, great. He just keeps on going. But if 2 of them happen to simultaneously transmit that dominant state to 0, who gets to keep going? Well, they'll both keep sending their IDs until the first one that drops out of the dominant state. So for instance, I'm sending 000, the next node is sending 001. The one that was sending 001 drops out of the dominant state. He says, oh, okay, so I'm a lower priority, so I'll stop. and then the one, and then, imagine that you have a large number of nodes that all might start sending simultaneously. One of them is going to have a higher priority in its ID, which is actually a lower ID value since it's really the zeros. The longer strings of zeros, the higher the priority, and it means I'm gonna hold out the longest where everybody else eventually sends a one, but I haven't yet, so everybody else backs off, so to speak. I hope that makes sense. I didn't explain it quite too well, but you can see it's very simple procedure actually. Now, earlier I mentioned regarding the number of nodes that can be connected. And really that's a factor of the time delay on the bus. So the distance between ends of the bus, if you want to think about it that way, the communication distance, how long it is, as well as the electric load, which is actually the speed, because the faster the speed, the shorter the bit time. So the less time that you have. So if you have a lower speed, you can tolerate a greater distance. If you have a higher speed, you're less tolerant of distance because the bits have to be wide enough to where they can get to throughout the entire bus before the next bit is sent. So it's kind of interesting. I mean, I hate to use previous analogies if you've not studied, like for instance, Ethernet, but if you ever did study the earlier versions of Ethernet and you ever heard of the 5-4-3-2-1 rule for determining how many segments of the bus can be connected by repeaters and blah, blah, blah. It all had to do with this, the speed as well as the distance.
And the intersyllable interference.
Yeah, exactly. And the interference, and to a certain extent, you might even say that the interference is not even a factor here just because of the way that the difference.
At these speeds, that's correct.
Yeah. All right. And then you can look at the community. I think I already really said what this last bullet is. Communication distance is inversely related to the communication speed. So it's just looking at a different way. The farther the distance, the smaller the communication speed, the longer the distance, but the speed has to drop down some. I won't spend a whole lot of time on this. For the most part, what you're sending are data frames. But there are actually 4 different types of frames that can be transmitted. A data frame, a remote frame, which you can use to solicit something from another node, an error frame, which the nodes can send when they detect an error in a message and make sure all the other nodes understand that was the case. And then an overload frame, meaning I'm too busy, so let's slow things down here a little bit. It's like flow control, if you ever studied that. I mean, a simple ASCII flow control is just an X on and X off bit, so to speak. Ethernet flow control was a specific pause frame. So an overload frame is a similar thing in the CAN world.
So remote frame is basically, give me some data, please.
Right. It's a type of message because it's a message without data. Yeah, exactly. All right, so now let's look at the data frame. The interesting thing about it is the data isn't just, if you want to say, one channel of information. It could actually be broken up into multiple channels and each one carrying, so within that 8-byte data field, you could actually have multiple things that are being indicated over separate, what's referred to as channels. So essentially, in this case, the data is from, I believe, probably the engine in this case, because it's sending out a CAN message, letting everybody on the CAN know what the current temperature and RPM level is. And that's actually sent in the same message. So it's based on, let me think about how to put this real quick in terms of, CAN messages, you got to be speaking the same language. And that language is programmed into this ECU, so they all know. Whereas a CAN frame is common to all languages, so to speak, but it's only how you program that. So it knows that these first 4 bytes are temperature and these next 2 are RPMs from this one specific ID. So it's all so it's Out of the box, it's not going to work that way. You're probably going to be speaking foreign languages to each other until the things are programmed all the same. So this actually is obviously talking about logging, and logging is done all the time. I mean, not just for your project. I know one of the reasons that you probably want to do it is because you want to be able to see if those messages that you're building are appropriate. So you want to have them logged somewhere so then you can download and analyze them. But in general, they're done all the time for normal processes within the car. Error messages. I mean, we're all familiar with, we get this little dummy light or whatever, error message in the dash that says service engine soon. Oh, great. we all love that one. And
You'd
so
rather
on.
know about it in advance
Exactly.
rather than a breakdown.
Exactly. Yeah. But it generally always means a trip to the dealership. But maybe after you're done with this project, you're going to know how to grab that data yourself and determine what it is. But not by my presentation, by the way, but what you're doing from this project. At least you know that you have the capability of doing so through this presentation. And so there's a specific port in your car. A lot of cars will have them on the left side of the dash where you pop off that. You open up the door, right? And you pop off that and you see a connector inside of there. That is an OBD2 connector. And that function there with the ODB2 connector could be like a built-in logger. Maybe it's not logging specifically all the CAN messages, but it's logging all the error codes and different codes that I guess it doesn't have to be an error code or whatever. And then you can plug into it and you can download that and analyze it. A similar thing has to do with the trucks and large equipment, which is like, so what you're working on, instead of OBD2, you're probably working with J1939. And I'll show you, there's a picture of the different connectors there that's used for heavy duty. And telematics is another way. It's actually in another extension. It's not just log this data, but send this data, typically OTA, over the air, which could be Wi-Fi, it could be cellular or whatever. So we can track that vehicle and everything going on with that vehicle, or at least what we programmed it to track. And that's referred to as telematics. Okay. And then I think, I'm not exactly sure who spoke up because I can't see who's speaking at the time, but you already mentioned predictive maintenance, another very, very good reason to be logging data and even monitoring and even sending that through over the air to the cloud, back to the dealership or whatever. So they can actually, let you know, hey, you better get the car in here pretty quickly because there's a problem developing. So we've been asked by SAE to work with you and identify a reasonable logger that you can use in your own development there in Washington, CAN bus data loggers. So this one is by CSS Electronics. It's called the CAN Edge 1. And as you can see, it's a really simple device. It's got the memory to store the messages, 8 gigabits, but it can have up to 64 gigabits of memory. It's got an SD card, which is actually that memory that we just referred to as. And the SD card, in this case, this particular CAN logger, the only 2 CAN ports it has are actually CAN ports. So there's really no way to connect it to your PC to program it. So this SD card functions as both the storage for the log messages, as well as you can plug it in your PC and you can use it to configure it. And what's to configure it? In this case, it may be, are we doing high-speed CAN, low-speed CAN, CAN classic, CAN FB, those types of things, as well as filters. You can set up filters so you're not trying to log every CAN message, but you're only trying to log certain CAN messages and so on. So that's done by sticking this SD card in your PC as well. And then the CAN data that's stored is in MDF4 standard, which is a popular standard, although there are other ones for, and I did document that in another slide, other formats, but that's the most common one that's used for CAN bus logging storage. This slide, I believe, just talks about the things that I notice. Those CAN ports can be CAN, CAN FD, and even LIN. Now, I brought this up a moment ago in terms of, well, how do you connect to the CAN bus yourself, especially when you're trying to pull this log data itself off the car? I mentioned on cars, it uses OBD2. Heavy duty vehicles such as trucks uses J1939. But there also, remember, there's other usage for this for CAN. So in maritime, CAN open. Now, contactless is interesting, and you'll see that in a moment. The same company that makes the CAN bus logger, the CSS electronics that I mentioned on the previous slide, also makes what they call a CAN crocodile, and it'll make sense in a moment why they call it a CAN crocodile, because it can essentially clamp on to the cables without breaking them and pull the signals out that way through induction, right? And there's other ways, customized cable connect, because these are standards. OBD2 is a standard connector, J39, 1939 is, and DB9s are pretty common in CAN. But what if, like I said, you could just splice into the wire if you want to. So let's see. I think this next slide gives you some examples. You know, you got your two-sided DB9 cable, and then this one, actually, the connector has a resistor, 120 ohm resistor wired between the CAN and high and low wires if needed. Again, it doesn't really hurt it to put a resistor at every node. It's just with high speed CAN, it's not required, but with low speed CAN, it is to make it more robust. Here is your J1939 cable that's used with the heavy vehicles like trucks and so on. So and then here is your ODB2 cable, which might look familiar to some of you. Have you ever popped off that panel in your car and you saw, oh, what is this thing? Well, that's exactly what it is. You can plug in there and grab all the data that's been logged on the vehicle directly. I point out this one here. This is one of those generic ones that I mentioned, because this is probably what we'll be using with your PCBA system with that CAN hat and the CAN logger from CSS Electronics to connect those together. And I'll show you an example of that in a moment. In this case, assuming, well, that's true, even for that CAN logger that we got, it doesn't have its own power supply. So in this case, we can grab the power off, however you're powering everything else in your system, to provide power to the CAN logger. And then this would plug into the CAN logger. And these are the twisted pair of wires that would plug into the CAN bus on your CAN hat unit. And again, I'll go for and show you that in a moment. And, you know, typical wiring adapter pinouts for the DB9. And this is pretty common, although I wouldn't expect it to be exactly the same in every implementation. So it's always good not to just assume that it's these pins and so on that are used, but to double check the documentation. So again, I mentioned CAN crocodile. So, and you can see this end actually looks like a head of a crocodile because it clamps down over the twisted pairs and can, through induction, it can pull the signal off of the wire. I wouldn't say, I would say that's morely for diagnostic type of thing. I don't think that you would necessarily do that in an operational vehicle, because you can, kind of like with that thicknet system that I mentioned earlier with Ethernet, if you start to wiggle it around, you might just start causing some problems or something. So, and notice one of them has the, if you need power to the unit that you're connecting to, it has also a power that would connect to the appropriate pins on the DB9. We're almost to the end here. I know, I think, I can't remember how long we scheduled, but we're almost to the end. So this kind of gives you an example. The CAN Edge 1, again, is the data logger that we'll be using. And you can see the different examples of how it's connected, whereas this example on the bottom is most likely what we'll be using with that. And this is just, I just threw this in here so you get an idea, you know, the log data. And again, most likely an MF4 format, but it can be converted to CSV and others formats if whatever your application requires. And this is just an example of the raw data, how it might be read out. And, you know, you can imagine that you need to, as a human being, you need to really understand, well, what does this ID actually mean? What does this data mean? Looking at the hex and so on. But the good news is there's obviously applications that'll convert that and put it in a more human readable format. So here's the example of using this. Here's the CAN edge. Here's the one custom cable that we talked about before. Here it is plugged into the CAN edge, and of course your system that has the PCBA with the Raspberry Pi and the CAN hat on top. Of course, you're probably familiar now. The Raspberry Pi on the bottom, the CAN hat plugged up on top. And then the way that we're going to connect in is we're going to just, well, obviously this end's plugged in here, and then these cables are going to plug into this is CAN 1. So this has a CAN high and CAN low, and this is CAN 2. So it also has a CAN high and CAN low, which, by the way, you can connect those back to back. And then in that case, instead of being two separate cans, it would be just one can. But the logic and why you would do that or whatever, I can't say, but that actually would work to do it that way as well. But this is the way, so that way, you know, you program through the Raspberry Pi to send out a CAN message on CAN 1. That's going to connect into the CAN logger. It's going to get logged. It's going to be placed on the SD card. And then when we're done and ready to look at things, we're going to pull that SD card out of the CAN edge, and we're going to plug it into our PC with that open source software to use for the analysis that I mentioned before. We'll also use that software to configure the CAN edge one to begin with. That was the last slide. So I love networks, networking, network protocols, all that kind of stuff. As you can sort of tell. So it was kind of fun for me to put this together because I've been involved with Automotive Ethernet to a certain extent for a few years, but not really to this level. So it was really fun for me to go through myself. I hope you guys think about it that way. I mean, if you're ever going to be successful in computer networking, cybersecurity, all this stuff, you got to really get excited and about it. And so try to keep up that enthusiasm. And yeah, it's my pleasure and nice to see you all.